Okay, so this calculation is going to have a lot in common with what we've already done in that previous example. So definitely look at that old example. Let me remind you the sort of the roadmap is we've got z is a function of x and y, right? But then x and y individually are functions of r and theta. And we've already written down the partial of z with respect to r. That's partial of z with respect to x, partial of x with respect to r, plus partial z with respect to y, partial y with respect to r, which if you write down shorthand notations and remember that x is r cosine theta, etc. You have this. So this is going to be our sort of starting point. Now what we've been asked to compute here is the partial with respect to theta and then with respect to r, and I'm just going to do it in the other order because you're allowed to switch the orders, and I'm going to compute the theta partial of this. Is that cool? Okay. All right, but let's not forget that it's very convenient to append our little roadmap up here, and note that I have zx and zy here, right? And I'm going to have to take some sort of various derivatives of them, and let's make sure that they're on the roadmap. So I'm going to observe that zx and zy are, well, they are also functions of x and y, just like we did in the previous problem. Is everybody good?
Yeah.
Okay. Right. So let's see, by the way, if I can do. Oh, nice. Okay, I didn't know I could do that. That's cool. Fun. Okay. So, yeah. Let me give myself a little bit more space by coming over here. And now I'm going to do second partial z, respect to r, respect to theta, and I'm going to take the theta partial of this business. Okay, and I'm going to have a couple of product rules that I have to deal with here. So first of all, I have let's look at this. This is a product, and I get two terms for that. So I'm going to have partial of zx with respect to theta times cosine theta, and then plus zx times the partial of cosine theta with respect to theta. So that's what that turns into, right? Okay. And then likewise for the other side. So I think what I'm going to do, by the way, is I'm going to do just the one term, and I'll let you do the other term, right? Okay. So I'll leave this one for you guys. Yeah. Okay. All right. Now some of this you can write down immediately. That's the good news. But so, for example, partial of cosine theta with respect to theta. That's an easy one, right? Okay. So what I want to do, though, is focus on what is going to be a challenge, and that is this, partial of zx with respect to theta. Now, a lot of students will write down zx theta. Well, that doesn't really make any sense, because look, z is there, x is here, and theta is there. So what do you mean z and then take the derivative with respect to, and then you have two different variables that aren't even in the same world. You can't really do that, right? But so what we're going to do is think of it as, which it is, by the way, zx, and we're taking a derivative with respect to theta. And this, you can see it's a chain rule problem because we have to step over two levels, and now we have to play pathway games. How can changes in theta propagate through and become changes in x? And, well, there's only two paths. There's what you might call the x path and what you might call the y path. Cool? Mm-hmm. All right, so with that in mind, we rewrite that guy as partial zx with respect to x, partial x with respect to theta, plus partial zx with respect to y, partial y with respect to theta. Now, before I get into simplifying that, let me just acknowledge that that is just what that became. So don't forget you've got to multiply it by cosine theta, and then plus zx, and then let's go ahead and simplify this while we're here. Partial of cosine theta with respect to theta is minus sine theta. That's right. So I'm going to say minus sine theta. Yeah. Okay. Good? Mm-hmm. All right. Now, let's simplify a little bit. This guy, that's zxx. And that makes sense because z is a function of x and y, and that just says take a couple of partials of z, both with respect to x. Partial of x with respect to theta. All right, well, let's see. Okay, x is r cosine theta, so negative r sine theta. Okay. Partial of zx with respect to y. All right, well, we'll come back up here. Partial of zx with respect to y. Well, again, fine. That's just zxy. There's no chain rule there. Zx is a function of x and y, so it's partial with respect to y. No problem. Yeah.
I'm not sure I really understand the zxx and zxy.
Oh, okay. Well, so if you have, let's see here, if you have functions, forget about the chain rule. Suppose there's no chain rule. It's just we have a function of x and y. You remember that if you take a partial derivative, that little subscript notation is just a shorthand for it. So, for example, if you have f is a function of x and y, then partial of f with respect to x, we just write fx. Right? And so that's what we've got here. Z is a function of x and y, so partial of z with respect to x, zx. Second partial with respect to x is zxx. It's just, yeah, it's just shorthand notation. There's no need to worry about, there is no chain rule involved there because there is no intermediate variables. It's directly partial derivatives. Okay. Yeah. All right. Okay. Reminder of where we were. That's that. That's that. That's that. Okay, now we've got to take, what's the partial of y with respect to theta? All right, y is r sine theta. So that gives me r cosine theta. Oh, whoops. Y is r sine theta, so yeah, r cosine theta. Okay, don't forget that's being multiplied by cosine theta. And don't forget that extra term over there. Now, by the way, I'm...
that's only the half.
Yeah, that's exactly. That's only the half of it. So I really should be writing as I go along here, you know, plus the other terms. You know. So, yeah. And you might want to simplify this a little bit. You know, you can distribute this cosine here, and you know, so you have zxx, r sine theta, cosine theta, and then you know zxy, r cosine squared theta. You know. And
then I could have, for example, the other part, the cyx with the zxy.
Yeah, I can't do it in my head, but yeah, there's going to be other. You can spec.
There's a partial of z in respect to x, and then y is the same as a partial of.
Oh yeah. Yeah, so zxy and zyx, you take it as the same because the assumption in this problem is that these functions are twice continuously differentiable. So yeah, totally. Yeah. Right. So at this point, it's just algebra. Is that cool?
Mm-hmm.
Yeah.
Okay. Bunch of algebra. So here's one of the big morals, by the way, of this problem. Why am I erasing that? I need to keep that there. But be careful. Don't try to do too much all at once. Now, I have the advantage when I'm doing this. I've got this cool little stylus and highlighters, and I can say, hey, by the way, you know, that equal to that. right? But as you're working, you don't have that convenience, and so you've got to keep it in your head. You might consider some other way of keeping track, and if you have a cool stylus, then you can do something like that. But of course, on an exam, you won't. So it becomes all the more important to double check everything that you write down, because it's really easy to it'd be really easy to just forget, kind of drop that, and something like that. The other thing is, I encourage you to try to write as neatly as you can. I like to make outer parentheses bigger and inner parentheses smaller. It's easier on my eyes, to sort of see what's going on. Otherwise, you might inadvertently forget that this doesn't just multiply by that term. It also comes over to that term, and it's easy to forget the other. Yeah.
So basically, for the next one, you would just do the same thing, except you'd use the first partial of z respective theta.
Yeah, it'd be yep, that's right. And of course, the algebra's all different, but yeah, that's right. Yep, and it's the same little diagram, right? And all exact same ideas, just different details.
Yeah. Is zxy the same thing as zyx?
For twice continuously differentiable functions, yes, and that was the intent in the question. Hopefully, I wrote that in the example.
So they have to tell you if it's twice continuous.
Yeah, I mean there are some obscure little weirdo examples where if you have functions that are, if the second partials are not continuous, it is possible to come up with an example where the xy partial and the yx partial are actually different. And it's hard to do. It's a trick shot, but you can do it. And so, in Math 212, we're not worried about that kind of thing. Right. Okay, is everybody happy with this question?
Yeah.
Okay, let me stop the recording.